Welcome to G Fun Facts Online. Today, we're talking about an ancient art form that's being supercharged with cutting-edge code to create a new class of materials that can literally build themselves. Imagine a flat-packed solar panel for a satellite that unfurls to its full size at the touch of a button, or a microscopic robot that assembles itself inside your body to deliver medicine directly to a tumor. Or even buildings with facades that ripple and shift to adapt to the sun's rays throughout the day. This isn't science fiction. This is the world of computational Kirigami, a field where the Japanese art of paper cutting is being translated into programmable, self-folding structures that have the power to reshape our world. For centuries, Kirigami, which comes from the Japanese words kiru for to cut and kami for paper, has been about creating intricate three-dimensional objects from a single sheet of paper. Now, you might be thinking of its cousin, origami, which relies only on folding. Kirigami is different because it incorporates cuts. These cuts give it incredible geometric flexibility, allowing for far more complex and dynamic designs. Scientists and engineers are now digitizing this ancient craft, using computer science to unlock its true potential for creating dynamic, reconfigurable materials. It represents a complete paradigm shift in how we think about manufacturing, robotics, and design. At the heart of this revolution is a fascinating computational challenge known as the inverse design problem. Think about it this way. Traditionally, a designer would create a pattern of cuts on a flat sheet and then see what three-dimensional shape it produces. It's a process of trial and error. But what if you have a very specific, complex 3D shape in mind? Say, a tiny, intricate medical stent, and you need to know the exact 2D cutting pattern required to create it when it unfolds. That is the inverse problem, and it's a puzzle so complex that it's practically impossible for a human to solve. This is where computer science becomes the hero of the story. Researchers are developing incredibly sophisticated algorithms, often using machine learning and genetic algorithms to crack this code. These computational tools can explore a mind-bogglingly vast design space, virtually testing countless cut-and-fold combinations to find the one perfect pattern for a desired outcome. The process is a beautiful dance between digital design and physical simulation. It begins with defining the target. A designer creates the desired 3D structure in a computer-aided design, or CAD, environment. This is the goal. Next, an optimization algorithm gets to work. Think of it as a tireless digital artist generating and simulating thousands or even millions of different 2D Kirigami patterns. It iteratively adjusts the length, position, and orientation of every single cut, inching closer and closer to a pattern that will produce the target 3D shape. Then comes the critical step: simulation and validation. Using powerful software like ABAQS or custom scripts, scientists simulate the deployment of the 2D pattern. These simulations, based on a technique called finite element analysis, model the real-world physics of the material. They account for its elasticity, how it will bend and stretch, and ensure that the final, deployed structure will be stable and behave exactly as intended. Once the simulation confirms that a 2D pattern will create the desired 3D form, the final digital blueprint is generated. This blueprint can then be sent directly to a laser cutter or another high-precision fabrication tool to create the physical object from a flat sheet. And thanks to software tools like Rhino 3D and its visual programming plugin Grasshopper, designers can create and parametrically control these Kirigami patterns, making the technology more accessible than ever. But creating the perfect pattern of cuts is only half the story. For a Kirigami structure to be truly self-unfolding, it needs a built-in trigger, a mechanism for actuation. It needs a way to transform from its flat, 2D state into its final 3D form without a person folding it by hand. This is where smart materials enter the picture, providing the muscles for the Kirigami skeleton. Scientists are embedding a variety of stimuli-responsive materials directly into the Kirigami designs, giving them the power to move on their own. One of the most common methods involves thermo-responsive polymers. These are materials that contract or expand when heated. Researchers create a layered material with a heat-sensitive polymer at its core. By running a tiny electrical current through specific parts of the sheet, they can generate heat, causing the polymer to contract and the structure to fold at precise points. The placement of these tiny heaters determines the folding angle, the direction, and the exact sequence of the transformation, allowing for incredibly complex, pre-programmed self-assembly. Other materials, like hydrogels, work in a similar way, changing their volume in response to stimuli like temperature or even moisture in the air. Then you have the really advanced stuff, shape memory alloys and polymers. These materials can be programmed to remember a specific three-dimensional shape. You can deform them into a flat sheet, and then, when triggered by a stimulus like heat, they will automatically spring back to their original, complex 3D form. It's like magic, but it's just materials science. Researchers are also using magnetic fields. By embedding tiny magnetic particles within the material, they can apply an external magnetic field to remotely trigger the structure to fold and unfold on command, with no physical contact needed. Of course, there's also the simplest form of actuation, mechanical force. By carefully designing the cuts, a 2D sheet can be made to pop up into a 3D structure just by being pulled from its ends. As Ji Yin, an associate professor at North Carolina State University, pointed out, this research represents the very first instances of 2D Kirigami patterns autonomously reshaping themselves into distinct 3D structures without any direct mechanical pushing or pulling. This ability to self-assemble is a complete game-changer, and it's unlocking a vast array of potential applications across almost every field imaginable. Let's start with soft robotics. Traditional robots are often rigid, clunky, and struggle to interact with delicate or irregularly shaped objects. Kirigami-inspired soft robots, however, are made from flexible materials that can conform to their surroundings. Researchers have developed soft grippers that can gently pick up anything from a single grain of sand to a full bottle of water. Their shape-shifting ability allows for a grasp that is both secure and incredibly delicate. These robots can be designed to crawl, twist, and bend, opening up possibilities for navigating complex environments, from search and rescue operations in collapsed buildings to performing tasks in internal medicine. Speaking of medicine, the biomedical applications are perhaps the most exciting. The ability to be fabricated flat and then deployed into a 3D structure makes Kirigami perfect for minimally invasive medical devices. Imagine a heart stent that is inserted into a blocked artery in a compact, flat form, and then, once in place, unfolds to open the vessel. Or picture a self-assembling container injected into the bloodstream that navigates to a specific site within the body and then unfolds to deliver a payload of drugs directly to a cancerous tumor, minimizing side effects. At Cornell University, researchers are developing Kirigami-based micro-robots smaller than a millimeter wide. These tiny machines can transform their shape and crawl, with the ultimate goal of navigating inside the human body to perform medical procedures with a level of precision we've only dreamed of. Then there's aerospace. Space is at an absolute premium on a rocket. Every cubic centimeter costs a fortune to launch. Kirigami offers a brilliant solution for packing large structures, like solar arrays, communication antennas, or even entire habitats, into a tiny volume for launch. Once in the vacuum of space, these structures could deploy to their full size on command. We've seen a version of this with the James Webb Space Telescope's magnificent folding mirror, which is a triumph of origami-inspired engineering. Kirigami takes this a step further, offering even more complex transformations from simple, cut sheets. The low cost and simplicity of some designs could also revolutionize the deployment of sensors, or even aid in humanitarian airdrops with self-deploying parachutes. The world of architecture is also being transformed. The facades of our buildings could become dynamic and responsive. Imagine surfaces that change their shape throughout the day to optimize sunlight exposure, provide shade exactly when it's needed, or control ventilation naturally. Researchers at MIT have used Kirigami principles to develop ultra-strong yet incredibly lightweight materials. As Assistant Professor Caitlin Becker at MIT suggests, building facades are one of the most promising near-term applications, making complex curved structures more practical and far less material-intensive. And for a truly mind-bending application, Kirigami is even being used to create computers that don't rely on electricity. In a fascinating twist, researchers at North Carolina State University have developed a mechanical computer using interconnected polymer cubes. These cubes represent data through their physical state, either up or down, representing a 1 or a 0. This form of mechanical data storage is incredibly stable and robust, immune to power outages or electromagnetic pulses. It could offer a completely new paradigm for data encryption and long-term security. Despite all this incredible progress, the field of computational Kirigami is still in its early stages. The inverse design problem for highly complex, multi-state structures, meaning a single sheet that can fold into several different useful shapes, remains a significant computational hurdle. Ensuring the stability of these structures and precisely controlling their deployment path is another key challenge that requires a deep integration of geometry, mechanics, and materials science. And, of course, the development of new smart materials with faster response times, greater durability, and a wider range of actuation is crucial for expanding the scope of what's possible. Looking ahead, the convergence of advanced manufacturing, computer science, and materials science promises an exhilarating future for Kirigami-inspired engineering. The ultimate goal is to create what scientists call pluripotent materials, single, reconfigurable patterns that can be manipulated into a dizzying array of different target shapes on demand. This could lead to electronic systems, where flexible mechanics are combined with onboard electronics to create materials that can respond to stimuli and reconfigure themselves in programmed ways, perhaps even at the speed of light. The journey from a simple paper craft to programmable, self-assembling matter is a powerful testament to human ingenuity. By writing the rules of folding and cutting into code, we are not just creating new devices, we are establishing a fundamentally new way to build the world around us. From the nanoscale to the architectural scale, the future is being cut, folded, and coded, and it is unfolding right before our very eyes.